Imagine a massive overhead crane, 40 feet in the air, slowly lowering this 5-ton aerospace engine block onto a solid metal table.
Oh, wow. Yeah, that is a serious piece of metal.
Right. This isn't just a heavy chunk of raw steel. This is a highly engineered, precision cast component destined for a commercial jetliner.
So we are talking about hundreds of thousands of dollars invested in a single piece.
Exactly. Now, picture a cutting tool approaching that block, spinning at incredible speeds. If the machine holding that massive block of iron shakes or, vibrates even a fraction of a millimeter during the cut,
That entire casting is instantly ruined. The money, the labor, all of it just gone in a microsecond of chatter.
it really is terrifying. So welcome to today's deep dive where we are stepping right onto that high-stakes factory floor. We've got a fascinating stack of technical notes today comparing two distinct layouts for horizontal machining centers, or HMCs.
Right, specifically the positive T-type and the inverted T-type.
Yes. And our mission for you today is to discover exactly how analyzing mass, motion, and gravity in these massive machines prevents costly manufacturing bottlenecks and, of course, maximizes a factory's return on investment.
When you look at a modern manufacturing facility, the sheer scale of the machinery can definitely be overwhelming. Beneath all that spinning metal and splashing coolant, there's a fundamental battle of physics taking place.
And the architectural layout of these HMCs serves as the actual battleground, right?
Exactly. What's fascinating here is that the choice of machine layout isn't just some minor preference. It dictates whether a factory remains competitive and profitable from day one.
Because it's about physical constraints.
Yes, it all comes down to the physical size of the part you are cutting and the floor space you have available to do it.
Okay, let's unpack this, because since we just talked about the absolute nightmare of ruining a 5-ton engine block, we should probably explore the machine designed specifically to stop that from happening.
Right, which brings us to the heavyweight champion, the inverted T-type HMC.
So break down the mechanics of this heavyweight for us. How is it built?
The inverted T-type architecture places the heavy workpiece on a very wide front bed that moves left and right. That's your x-axis.
Okay, wide front bed. Got it.
Then, it places the vertical column, the part holding the cutting tool, on a rear bed that moves front and back. That is your z-axis.
I think the best way to visualize this low center of gravity is, well, to think about human stances.
Okay, how so?
Like, imagine you are trying to hold a massive, heavy boulder in your hands. If you're trying to carry that boulder while standing straight up, feet close together on your tiptoes.
You are going to topple over the absolute second someone bumps your shoulder.
Exactly. Your center of gravity is totally wrong for the load, but if you drop down into a wide, extremely stable sumo squat, planting your feet far apart, you are completely rooted to the floor.
I see where you're going with this.
Yeah.
The inverted T-type is essentially doing a mechanical sumo squat with a 5-ton piece of solid iron.
Yes. So how do the engineers actually build that mechanical sumo squat? They don't just pour a giant block of iron and hope for the best, do they?
Not at all. Engineers use advanced software to optimize a complex network of internal iron ribs inside that machine bed. It achieves a massive static rigidity of over 250 newtons per micrometer.
Wait, 250 newtons per micrometer. Give me a visual for that. Say I push against that cutting spindle with the sheer weight of a Ford F-150 pickup truck.
Okay, that's a lot of lateral force.
Right. So how much does the metal of the machine actually bend under that truck's weight?
Practically nothing. We are talking about deflecting by a fraction of a single human hair.
Oh, wow. That is just absurd rigidity.
It really is. Now, for the operational benefits, because the spindle column is mounted on the rear z-axis, it's the mechanism actively pushing the cutting tool forward.
And the brilliant part is that the physical weight of that spindle box never changes.
Right, exactly. The servo motor pushes the exact same weight every single time it moves. The pushing force remains perfectly consistent, so you can drill deep, wide holes perfectly without the physics ever fluctuating.
And for the listener, the practical benefit here is huge. Having that heavy workpiece sitting right on the wide front table allows for incredibly easy and safe overhead crane loading.
Right, you just drop the part right onto the front rails.
So what does this all mean if you aren't building giant aerospace parts? Like, what if you just need to manufacture tiny medical parts, say bone screws, by the thousands?
Extreme rigidity is great, but in that scenario, the heavy machine moves too slowly. It completely kills your batch production times.
Right, it needs speed.
Which brings us to the speed demon, the positive T-type HMC. This machine achieves extreme velocity through a completely different structural mechanism. It completely decouples the axes.
Decoupled axes. I want to visualize this. So instead of stacking movements on top of each other, they're completely separated on the floor plan.
Exactly. The column moves left and right across the base on the x-axis. Completely independent of that, the table carrying your tiny titanium screw moves forward and backward on the z-axis.
Because no servo motor ever has to carry the weight of another servo motor.
Precisely. They are isolated.
I see. Because pushing a massive, heavy machine structure just to maneuver a tiny titanium screw is a spectacular waste of energy. It would be like using a heavy freight train to deliver a single pizza.
That's a great analogy.
You have all this power, but the sheer weight of the delivery vehicle slows you down. By only pushing the tiny workpiece, the table's physical inertia stays extremely low.
Right. The machine achieves explosive tool feed acceleration. It darts back and forth, picking tiny holes in milliseconds. You save massive amounts of time on every single part.
But hold on, you're telling me a machine carrying a heavy iron spindle is darting left and right at, well, the notes say 1G of acceleration.
That's right, 1G.
That sounds physically impossible to manage. Wouldn't the violent momentum of that heavy column stopping and starting literally walk the massive iron base right across the factory floor?
That is the defining engineering challenge of the positive T-type. But here is the trick. That column weight never, ever changes.
Because the part being cut is on the other axis.
Exactly. Because that mass is a constant known variable, engineers can tune the electrical servo parameters to their absolute maximum limit. The software knows exactly how to stop that specific mass on a dime.
But the physical iron structure still has to absorb that violent kinetic energy. How does it not vibrate and ruin the cut?
Builders use differential height rails, or an equilateral triangle support structure within the iron base.
Okay, an equilateral triangle. How does that help?
Rather than placing the guide rails on a flat plane, where forces could cause the blocks to rattle, the triangle distributes lateral shock downward, driving it deep into the foundation.
Ah, I see. And the differential height rails?
They act almost like a banked curve on a racetrack. They lean into the directional thrust when the column stops instantly. The solid iron rock absorbs those violent 1G shocks perfectly without vibrating.
Here's where it gets really interesting, though. We've been talking about the clean, theoretical physics of these movements, but manufacturing is an incredibly messy reality.
It really is. The byproduct battle is constant.
Right. Whether you're doing massive heavy cutting or those violently fast precision cuts, both generate a massive shared problem: metal chips.
Oh yeah, metal chips are the silent, inevitable killers of horizontal machining centers.
Because you're cutting hardened steel, right, you generate massive friction, and therefore you create these mountains of razor-sharp, incredibly hot metal chips.
And if those chips don't clear out, if they just pile up inside the machine, they essentially act like a space heater sitting directly on your precision guide rails.
Which sounds disastrous. You're basically cooking your own machine.
Exactly. That heat transfers into the iron bed, causes thermal expansion, and the rails literally warp. A perfectly straight cut turns into a curve, completely destroying the machine's accuracy.
So you have to get rid of them instantly. And this is where the inverted T-type wins this contest easily, doesn't it?
Hands down. It fundamentally changes the geometry of the space underneath the cutting tool. The inverted T-type has a narrow upper structure, but the space underneath flares out into a wide open bottom.
So there's a direct, natural falling path.
Yes, gravity simply pulls the heavy hot chips straight down into the center conveyor channel. Tests show a consistent 20% increase in chip removal efficiency.
Because there's no physical iron shelf for the chips to get caught on, and I imagine that open design helps with coolant, too.
Absolutely. It provides excellent coolant access for flushing out deep cavities inside engine blocks without splashing back against internal machine walls.
Now contrast that with the positive T-type. How does that layout handle this avalanche of hot chips?
The positive T-type heavily struggles here. Because of its standard T-shape, it requires much wider upper guide rails to support the fast-moving table.
Ah, I see the geometry problem. Those wide upper rails sit right under the cutting action. They slightly block the natural falling path of the chips.
Exactly. The machine tries to compensate with steep iron channels, but it relies heavily on strong external auger conveyor motors to actively pull the chips out.
So chips might actually pile up during extreme heavy cutting because gravity is blocked.
Yes, which makes it much harder to keep clean compared to the inverted T-type, which just uses gravity for free.
If we connect this to the bigger picture, a machine's internal design directly dictates its external footprint.
Right. Which brings us to the ultimate real estate dilemma. For a factory owner renting a small building, floor space costs a staggering amount of money.
You have to squeeze absolute maximum production out of a very small room. So how do these footprints compare?
Well, let's look at the inverted T-type. It features a wide, heavy iron base bolted directly to the concrete floor and a narrow top.
So the upper moving parts are tightly compacted together.
Yes, this lower profile, highly compact footprint keeps the center of gravity low and integrates easily with factory automation, like robotic pallets.
You can fit more machines into your layout, but wait, I'm just realizing the incredible irony here regarding the positive T-type footprint.
What's that?
Well, the positive T-type needs those wide upper guide rails for the table and a narrow base underneath. So you're left with a giant top-heavy mushroom of a machine.
That's a very accurate description.
It's specifically designed to cut tiny lightweight parts, but it requires a massive bulky footprint that wastes valuable floor space and blocks walking aisles.
It is the ultimate engineering trade-off. You are trading real estate for velocity.
To summarize all of this for you, for fast, small, precision batch parts, you really want the decoupled speed of the positive T-type HMC.
But if you are wrangling heavy parts, fighting hot metal chips, and trying to save tight floor space, the rigid, gravity-friendly, inverted T-type HMC is the path to higher profits.
You engineer out the bottlenecks before the machine is even bolted to the floor.
This raises an important question, though, as we close out our analysis. We've seen how these machines are meticulously sculpted around constraints like gravity, metal chips, and part size.
Right, the traditional constraints.
But as we move into an era of 3D printed metal components and completely new ultra-lightweight synthetic materials, how will the very architecture of these machines have to evolve next?
Oh, that's fascinating. If the parts weigh a fraction of what they do today.
Exactly. Will the traditional T-shape, whether positive or inverted, even survive the next industrial revolution? Or will engineers have to dream up an entirely new geometry for the factory floor?
That is something to really chew on. Next time you hold a perfectly machined metal part, remember the hidden ballet of iron and physics that brought it into existence.
And remember the difference between balancing a boulder on your tiptoes and dropping into a sumo squat.
Thank you for joining us on this deep dive into the source material. Keep exploring, keep questioning the hidden engineering that shapes our world, and we will catch you next time.